Hello friends, today we are going to discuss one of the important topic AFLP PCR technique, amplified fragment length polymorphism PCR domain. You know, AFLP PCR, amplified fragment length polymorphism. You know, before going to the main topic, we have to discuss about certain basics. You know, what are DNA markers? DNA markers are essentially involved in genetic mapping. Genetic mapping is nothing but identification of approximate location of gene locus or the distance between the two gene locus. It has a huge potential role in forensic analysis and the phylogenetic analysis. The most commonly used DNA markers are RFLP. We know that restriction fragment length polymorphism we have discussed in last class. VNTRS, variable number tandem repeats. Then SNPs, single nucleotide polymorphisms, and short tandem repeats, STRs. Here VNTRS are otherwise called as mini satellites, whereas STRs are otherwise called as macro satellites. And they have a huge role in genetic mapping. And what makes them so unique and what makes them so potential? Because of differences in the restriction fragments. This is very important. Say for example SNPs, single nucleotide polymorphism. SNPs leads to variations in DNA fragments. Say, what are SNPs? A particular person, say me, have a particular nucleotide at a specific position, say cytosine. Some other person may have some other nucleotide base, say for example guan, so G base. Some other have T base, some other have A base. That means it all leads to variations in the restriction. That means different sizes, different length of the DNA fragments. And there are so far 3 million SNPs. DNA contains 3 million SNPs and they are potential DNA markers. And they are served as a huge, that means they are the huge resources base for forensic analysis and the phylogenetic analysis. Under this domain, we have discussed about PCR in the previous classes. You know, polymerase chain reaction. We can get n number of copies, say based on the sequences, in the sequential cycle, say denaturation, renaturation, synthesis. And we have discussed at the time that there are different varieties, there are different domains of PCR, like inverse PCR, anchored PCR, reverse transcription PCR, real-time quantitative PCR, RAPD, random amplified polymorphic DNA, RAPD PCR, and AFLP, amplified fragment length polymorphism, even RACE, rapid amplification of cDNA ends. These are different PCR varieties. And in the present class, we will discuss about AFLP PCR, how AFLP markers serve as a potential tool, that means a DNA marker in this PCR. Okay, we'll discuss one by one how this plays an important role in PCR technique. How this technique emerges? Actually, it is not a conventional technique. It's a hybridized technique. What exactly the hybridized? It is a combination of RFLP, restriction fragment length polymorphism, and RAPD, random amplified polymorphic DNA. You know, that means RFLP and RAPD leads to AFLP. How? In which strata does it correlates with RFLP and in which strata does it correlates RAPD? So just like in case of RFLP, it uses restriction enzymes. Restriction enzymes are nothing but molecular scissors we have discussed. They specifically cut the DNA. Say that there are certain recognition sequences. For example, ECORI, that means ECOR1 or MSC1. They identify a particular sequence, what we call palindromic sequence. That means the DNA sequence which repeat the same in both strands in a certain direction. and the most importantly, they leads to generation of polymorphs. They have potential in identification of polymorphs. But what is polymorphic DNA? That means it's different structure of DNA or DNA having different lengths. Because why they got, that means why different DNAs have different DNA lengths? Because of, say SNPs. See, that's how the connection SNPs leads to different, for example, for instance, SNPs leads to different DNA fragments, what we call polymorphic DNA. That means variations in the pattern of DNA is polymorphism, and this identification of polymorphism is one of the objective of AFLP, and this identification leads to forensic analysis and a phylogenetic analysis. That's the whole crux point of this AFLP PCR technique. As I said, in terms of RFLP, it uses restriction enzymes to produce restriction fragments. With respect to RAPD, it uses a random primers. Random primer, that means through which we can get number of amplification through PCR by the aid of random primers. So random primers leads to, that means enabled PCR amplification. In that sense, it uses RAPD, and with respect to RFLP, it uses restriction enzyme that leads to production of different restriction fragments. What we call, because of polymorphism. These are all interconnected topics. Okay, polymorphism. That means how SNPs are emerged. They're nothing but mutations. Because of how the DNA emerges. Even they had an important role in evolution of DNA as well. Accumulation of these repeated sequences over a period of time, what we call trial and error method, that leads to ultimate generation of a quality product. That means gene bearing sequences. It's around 2%. That means say 30,000 to 40,000 genes are there in respect to human genome. That means only the slightest contribution because of this, accumulation of their repeated sequences SNPs. How the issue ends. And regarding the protocol, we will discuss how this technique plays and work on the principle we will discuss about. Say we have isolated a particular genome, say from X source. This is the genome. Isolation of genomic DNA, and next important step is there are recognition sequences, say for restriction enzymes. Say this is for E core 1, and this is for MSE1, and these restriction enzymes, as I said, they specifically identify a sequence, what we call restriction sequences, recognition sequences, so that they will cut down the sequence, that means DNA accordingly, so as to get smaller fragments. Okay, the next step, it leads to smaller fragment. That means say how it works. Say with respect to E. coli, the recognition sequences for E. coli is G A A T T C. How we have to remember this? Get an apple to the class. Say get an apple to the class. G A A T T C. It's it's like a hint to remember this, which I have browsed from different sources, but through which we can identify this particular sequence. And then I told you this is a palindromic sequence now. So G A A T T C. This is 5 prime. This is 3 prime. And how about MSE1? The same in case of MSE1, there is T T A A. This is the recognition sequence for, you know, MSE1. And where it cuts, say with respect to E. coli, it will specifically cut here. With respect to, you know, the MSE1, it will cut here. I told you already, restriction endonucleases leads to generation of sticky ends. Sticky ends, the entire successful nature of our DNA technology in particular and the biotechnology in general is because of the sticky ends. Without sticky ends, you cannot expect chimeric DNA. And without chimeric DNA, you cannot introduce into the respective vector. And without this, you cannot expect a number of copies of desired gene, for example, insulin gene. That means generation of chimeric vectors. That means, say you take a plasmid and you cut down the plasmid with respect to appropriate restriction endonucleases, the generation of these sticky ends, and you incorporate the specific desired gene sequence by so that these two attach by complementarity, what we call it's about basics. Okay, that means this such a huge role of sticky ends or cohesive ends. And as I said, this is for E. coli. And this is for, you know, MSE1. The specific recognition sequences of these two restriction enzymes that ultimately leads to, obviously, you know, the different ends. This is the second step, what we call, you know, that means the restriction activity. Restriction activity. Okay. Then it leads to production of different fragments, smaller fragments. But the thing is, we have to ligate with adapters at both ends. At both ends. Here, this is very important. The third step, adapter ligation. We want to discuss this particularly, you know, what are adapters? Adapters are nothing but they are short, double-stranded DNA fragments having 5' overhangs. Adapters are nothing but they are the short, double-stranded DNA fragments with 5' overhangs. You know, because I told you already, the sticky ends have 5' overhangs. So according, that means they should be complementary so that there will be, that it enables to bind with appropriate complementary base pairs. So that's how they play an important. Adapters, the name it implied. Adapters, that means plug, the hole. The same concept, the short DNA fragment with having 5' overhang so that it will leads to establishment of complementarity with that of the 5' overhangs of the restriction fragment. This is very important. The adapter, which is short double-stranded fragment with 5' overhangs, which leads to establishment of complementarity with that of the 5' overhangs of the restriction fragment. That means restriction fragment sites. The same here. And that means there are specific adapters for ECOR1 and MSE1. This is very important. So say I have done specifically, this is for ECOR1, this adapter as told you double stranded, and this is for MSE1. These are two restriction enzymes, and according to the two adapters, corresponding adapters, one for ECOR1 and one for MSE1. That leads to plug the gaps. You know how it went. Ligation. So we know the DNA ligase is an enzyme that covalently connects these two. That means adapter with that of the sticky ends of the restriction sites. This is very important. This is what we call adapter ligation. The third step. And the fourth step, this is very important, what we call pre-amplification. Pre-amplification. The sense this pre-amplification means, say this is the target sequence template, you know, and this is for ECOR1 and this is for MSE1. Here what happens, you know, primer two primers. Just like we have two restriction enzymes, two adapters, for instance here, and two primers. One one primer for ACOR1 and one primer for MSC1. But the most important thing here at this point is the primer should have a selective nucleotide. That means each kind, a selective nucleotide at the 3' end. The end denotes that. Here we have added one selective nucleotide, that is what we call pre-amplification stage. Here, why this step? This is a most essential component of AFLP. Amplified fragment. We don't want the amplification of anti-genomic DNA, but we want selectively amplify some DNA fragments, not the selective amplification. This is very important. That means you got some DNA fragments and you selectively amplify the same. And how we can achieve that? How we could accomplish this task? Simply by addition of selective nucleotide at the 3' end of the specific or the respective primer. Say the primer for ACOR1 and the primer for MSC1. The end denotes that. And how it ends? Then what we call selective amplification. The next step, we add additional selective nucleotides. Say 2 selective nucleotides, 3 selective nucleotides. Likewise, we get a amplified product. It means amplification of some DNA fragments. That is how the issue ends. Simply the bottom line is saying that the first step is this, then the fifth step I told you now, the selective amplification. Selective amplification. Say how it ends. This is nothing. Say this is the target sequence. Then this is for ACOR1 and this is for MSC1. Just you need to add additional nucleotides. That's it. Here is one. The end denotes addition of selective nucleotide that leads to selective amplification of the respective fragments, or what we call amplified fragment length polymers. Restriction fragments, that restriction enzymes we use, and you also use the random primers. But here the thing is you add subsequently. The first one nucleotide you add, then additional you add, likewise you amplify some DNA fragments. So the bottom line is same. The first you isolate the genomic DNA, then identify, that means use the two restriction enzymes for typically two, generally we say ACOR1 and MSC1, identify the sequence, they will cut down and reach to sticky ends and do adapter ligation. This is very important. Just like plugging the hole. Specific adapter ligation, that means adapters for ACOR1 and adapter for MSC1, and these are short DNA fragments, double strand DNA that will plug the hole. Then after that you add the RNA primers of specific to adapt. That means corresponds. That means the primers are complementarity to the adapters. This is very important. I told you that means establishment of complementarity is very important. And the primers which are corresponds to the complement to the correspondent primers. The adapters, say ACOR1 and MS1 will add, and selectively you have to add the nucleotide at 3' end. What we call pre-amplification. Then we add subsequent nucleotides. That means at the 3' end of what we call selective amplification. So that all leads to generation of amplified products. What we call amplicon. Amplicon is a generated product of PCR application. The last step, the sixth step, the most important, electrophoretic separation and autoradiography. Say we have discussed in the previous classes, the shorter fragment, the lighter fragment, they move farther, whereas the heavy fragments they travel less distance. Say there are shorter fragments and there are some heavier fragments, and these are how for understanding I am saying, okay. Gel electrophoresis separation, that means agarose gel. Then autoradiography. You know, the funnest step, of course, the main objective you have to identify the polymorphic DNAs. Say I may have my own what we call DNA fingerprints. I may have my own DNA fingerprint that leads to DNA profiling. That means these DNA fingerprints are unique and specific to the individual belonging to a particular species. So with this technique, you are how do you establish? Just need to identify the polymorphs and how they generate, for example, SNPs. So they're specific and unique to individual in a human being. So this the same concept you can get applied to some other individual and apply to the ultrafluorescence run, and you will get the specific banding pattern through autoradiograph you can visualize, because each and every individual have its own DNA profiling, own DNA polymorphism. I told you already. I say SNPs. I may have a one particular nucleotide at one position, other individual X individual have some other nucleotide. So it leads to creation of 3 million SNPs in human genome. So this is how this polymorphic DNA plays an important role in generation of DNA fingerprints, individually within a species and even with closely related species also. We can establish phylogeny. That's what I told. This plays an important role. This technique plays an important role in forensic analysis and phylogenetic analysis. The corresponding is same, the polymorphic DNA. No two individuals have same set of DNA pattern. They have differences. Okay. So do you track those by means of autoradiography? So visualize the banding pattern. So this is the final step. So I told you if the PCR, there are different techniques of the types of PCR like AFLP, RACD, REPD. The next class we'll discuss about REPD. All have a potential role in forensic analysis, like even crime, even that's like parent kids misplacement in hospitals. Even during this at these crucial times also this technique plays an important role. So it's about AFLP, that means amplified fragment length polymorphism PCR technique. In the next class we'll discuss about REPD. Okay.